Welcome to the High Field Magnet Lab. I'm standing here next to a magnet and, well, as the name suggests, what we're doing here is we're studying molecules and materials in high magnetic fields. Our highest magnetic field, which we can get now, is 38 Tesla. We're doing this analysis with a couple of different methods, for instance spectroscopy, with lasers, or with electrical transport measurements. So, what I do in my master internship is I'm looking into magnetostriction. What this is if you put a material in a magnetic field, its length changes. This length change is very small. It's about 1,000,000 times smaller than the length of the sample. And I find it very interesting how you can even measure these very small length changes. Why this is interesting is that you can learn a lot about the electrical properties of the sample, even if your sample does not conduct electricity.
I did my master's research at USCM, where I was studying magnetic materials. They are composed of spins, and if you shoot a laser at them, these spins can start to precess. These precessions propagate through the material just like a wave and produce oscillations. We are interested in studying these oscillations, but they occur at an ultra-fast timescale at 10 to the minus 12 picoseconds. But how do we measure such short oscillations? We do this with the so-called pump probe technique, and it works very much like making a movie. So usually you would follow a moving object along and take a picture at each time frame. But because the oscillations are so fast, we can now only take one measurement per movement. So we have to excite it multiple times and then take measurements with various time delays. And by this we can reconstruct the original oscillation. But why would we like to study such ultra-fast oscillations? Well, magnetic materials are, for example, applied in hard drives, which encode bits, zeros and one, in domains of magnetization up and down. And traditionally, to switch between these two domains, you apply a current. But we would like to do this by shooting a laser at the material, and this can potentially be much more energy efficient and faster. What I really like about this research is that it actually is really fundamental, but it still shows us how this can be important for future technologies.
So I did my master's project here at the Theory of Condensed Matter department, and my master project was about superconductivity in atomically thin 2D materials, and more specifically about what the effect of the environment is. And this is really important because experimentally these 2D materials are often encapsulated in other materials. And we now believe that these other materials can have quite a strong impact on the physics going on in this material. So to understand what the experiment gives you, you also need to understand the effect of the environment. But like this, I think that theory can help understand on a deeper level what is actually going on in materials.